Thank you very much for the introduction, Geert. I'm happy to be here. I'm not a signal processing person, so my talk will be slightly different in the setting and the wording what you're used to, right? And first of all, I'm going to start with a simple definition of what I consider as a network, right? A network is basically consisting in two items: an underlying structure, like you see the graph, actually the simplest things, the hardware, what you see, what you can absorb, and the more complex thing, the process. And one of the things what you see in the graph here is that the graph, and that's probably an important thing, the graph consists of nodes and links. And the graph, or the structure what you observe, is undirected. The directionality is given by the process. And that's probably an important thing. So the process, and just look to a transportation network or a street map. If you look to a street map, you just see streets. And it is the traffic rules that say in which direction you can actually traverse the streets. Yeah. So, and network science is quite new as a science domain, about 20 years old. And it is, in short, the theory of processes in and on graphs. And the duality between the structure and the process is actually the cornerstone and the key. Okay, this is a short introduction. It's a bit different than how you look to graphs from a signal processing point of view. I've chosen to talk about linear processes, and my talk is divided in two parts: discrete linear processes, which are easy, and then the stochastic ones, which are a little bit more complex. So we start easy. As a kind of an introduction, I know that most of you know what is the Laplacian of a graph, right? I call the Laplacian of a graph Q. Yeah, Q. It comes from actually graph theory and also from Markov processes, where it is related, as I will show with the infinitesimal generator. So you have an undirected graph consisting in capital N is 6 nodes and capital L is 6 links. The definition of the Laplacian is what you know is actually the diagonal operator, the diagonal matrix of the degrees. So this is the degrees of all the nodes, and A I use as the adjacency matrix. This is the incidence matrix. And if you are very quick, then you observe that the first node, the first row here, the degree is 3. You see 3 outgoing links. And then it is minus the adjacency matrix here. So I don't think this is rocket science. You have all seen this. One of the things that I try to stress is that there is a unique basic property of all Laplacians, and that is that if you multiply the Laplacian by the 1, 1, 1 vector, right? I call it U, also different in your notations. So the U vector is the 1, 1, 1 vector. That is a basic property. So it means that actually the column sum or the row sum of any Laplacian is always 0. That's a fundamental property. And it even holds for Laplacians, why here the Laplacian is undirected, so it's a symmetric matrix. And that's why I like symmetric matrices. Why? Because in the spectral domain, everything gets easy. This property I'm going to use several times. Okay, so this is a kind of an introduction setting the terminology. I use a D for degree. The delta I use, well, basically it's a diagonal matrix. I use the A for an adjacency matrix, and I use a Q for a Laplacian matrix. And the matrices that I'm using are all symmetric matrices because the underlying structure of the graph is inherently undirected. I come to that point later on. So simple things is linear dynamics on networks. I start with a linear dynamic process, and I mean that the process is proportional to the graph. What do I mean? So you have two nodes in the graph, I and G. You inject, let's say, a current or a flow. The flow traverses over a link. Think about a water network. So it's a pipe. The water flows through the pipe. And you can denote then the amount of water that is flowing by Y sub IG. And the the flow or the amount of flow that is flowing through the pipe, injected here and there, the amount is proportional to the height, basically, of the tubes. So that's not rocket science. And we call this the potential or the height of the nodes, and the difference of them is proportional to the flow. So this is actually a very basic thing, even what you've seen in high school. Yeah, you have water flowing through water or glass flow, and then the potential is called and the pressure. You have displacements in the spring, it's force. Here, because I'm part of electrical engineering, I look to electrical currents, and so then the potential difference, or the potential is the voltage, and the current through it is the flow. So the interesting thing is that the proportionality here of the process, and the process is here, well, the flow of water and the potentials. So the injection of the relation between X, which is the flow of something into the network, and then the process, which is steered by the potential. That's actually a simple proportionality relation. Yeah? You see that the injected current, even a vector, is proportional to the nodal current, and the proportionality constant between quotes is the matrix, and the nice matrix is the Laplacian. Yeah? And this holds in a lot of things. So if you have that kind of a relation, which is easy, then the next thing is that we are going to use reverses. If you have the current voltage relation, which I've shown to you, well, I didn't derive it, but you might believe that it's a correct relation, then you can actually turn it around and you can ask, even if I have only the injected current, what is the voltage? And then you use the inverse relations. And the inverse relation is a little bit complicated because I showed you in the first slide that the Laplacian, well, has a zero eigenvalue. So it means it's a determinant. The determinant of the matrix is zero, so you cannot have the inverse, but you can do a pseudo-inverse. Forget a bit what is the pseudo-inverse, but you can actually think about this relation as being just the inverse. The only thing is that with the pseudo-inverse, there are restrictions coming up. And the restriction all have to do with the U vector, which is the basic eigenvector belonging to the eigenvalue 0, right? And if you multiply both sides here by the U vector and you take the scalar product, yeah, then you know that the scalar product, because it's a U vector, is always 0. So the first relation here is that the scalar product with the injection current is 0, and that should be, because it's the conservation of currents. It's a fundamental law in physics. So that's important. And the second one, if you do it, then you have actually a kind of a constraint where you can use those relations. You actually impose that the average of all the potentials must be 0. So in other words, if you use as a reference potential, because the physics is always the potential difference, you have a difference. So if you use the potential reference equal to the average potential of all the nodes in the network, then you're in business and you can use these inverse relations. These relations are actually quite interesting. You will see. I will give an example of these relations, and this is probably a little bit terminology. The pseudo-inverse can be relatively easily computed, because if you have a symmetric matrix, you can always, in a very easy way, and also numerically stable, finding the eigenstructure. So you have here the orthogonal eigenvector matrix. This M is the diagonal matrix with the eigenvalues of the Laplacian. I call them mu. Mu1 is the highest one. Mu n, capital N, is always 0 and is the lowest one. And of course, this is the eigenvalue equation. If you write this equation in a vector form, you have this expression. And from that expression, probably the easiest way to compute a pseudo-inverse is you take 1 over the eigenvalues. Mind you that here, we do not sum over the n eigenvalue, capital N, because it's 0, right? So this already is again a reflection that there is one direction, the 1, 1, 1 vector, that is ignorant in the underlying structure of your Laplacian. Okay, for most of you, that's a bit basic. Yeah. So now I take a kind of recursion because I've been thinking, okay, people of signal processing, they are very, well, this is all elementary for you. So I'm now trying to talk about 3 equivalent representations of an undirected graph. The one is the topology domain. That's what I showed you, the toy example. You can represent it by an adjacency matrix. The second one is the spectral domain. Again, here my matrices are symmetric. So in a symmetric matrix, again, I keep stressing this, the eigenvalue decomposition and eigenvalues is just beautiful. If you depart from symmetry, it gets complex and less beautiful. So here, for the adjacency matrix, I have X as the orthogonal eigenvector matrix, and here the diagonal matrix is consists of all the eigenvalues. I think this is pretty standard, right? And in signal processing, you think about the time domain, and you think about the frequency domain, and that is what is probably the strength of this community, switching between these 2 domains. And you can do it in the graph domain. You switch between the topology, well, I call it the topology domain because you can draw it, you have nodes and links. And in the other domain, you have eigenvectors and eigenvalues. Okay, and that is a nice strength. And you know much better than I do that some problems are more easily solved in one domain than in the other domain. And it's the ingenuity to find in which domain you actually prove or solve the problem best, right? So these are 2 domains. Probably many of you or none of you know that there's a 3rd domain, which is completely also equivalent. So all the information maintained in the domain can be transported on another domain. And that is the geometric domain. In any undirected graph can be represented as a simplex in the n-dimensional Euclidean space. Who have heard about this? Okay, already a couple of. I will show you intuitively as a reminder or as an introduction, where does it come from? Yeah. So first of all, what is a simplex? A simplex is simply saying a generalized triangle. Yeah? And why is geometry so interesting? Well, it's the oldest mathematical sport or domain that we have seen. So many of the problems with triangles can be solved elegantly. How did we come actually to the notation or to the insight that you can present a graph as a geometric object? Well, you start with Laplacian. Yeah? I said already that the Laplacian, which is a symmetric matrix, can be decomposed in an eigenstructure. The very important relation here, keep that always in mind, that this is 0. And since it is a symmetric matrix, we know that the eigenvectors are all orthogonal. And an orthogonal matrix actually satisfies this kind of a structure. So I write it in full. So here, this is the eigenvector in this column with the belonging to the eigenvalue mu1, the highest one. This is the second one, and this is the last one. Yeah, and since the last one here is 0, right, or is, well, the eigenvalue is 0, but the eigenvector is the 1 vector, which is normalized, yeah, because it should be here normalized. It is 1 over square root of n, right? So in the rows here, yeah, we see the nodes, and that's the index here that I used. And in the columns, you see the eigenvalues or eigenfrequencies, if you wish. Okay? So what is now nice on the Laplacian matrix, it is a semi-definite matrix, meaning that all the eigenvalues are non-negative. There is always one surely which is 0. If there are more 0, then you have a disconnected graph. Okay, so here I assume that you only have 1 0 because we talk about a connected graph. So only for a positive matrix, you can actually take then the square root of the diagonal elements, yeah, because you stay then in the real domain, and you can write it as this kind of a representation. And if you now say that the matrix, we define the matrix S as being the transpose of the orthogonal matrix in the columns here, multiplied by the square root of the eigenvalues, right? Then you see that the matrix Q, the Laplacian, can be written as a kind of a Gram matrix, meaning that if you have S and you take S transpose and multiply by S equals the Laplacian. It's not rocket science yet, right? But it's nice. Yeah? And you observe that the S matrix has rank n-1. And that is due again to the basic property that there is always a zero eigenvalue of the Laplacian, right? So it means, and keep this in your mind, I will use that equation later on. Also, if you have the S matrix multiplied by the 1-on-1 vector, the U vector, it is 0. So I write the S matrix now, and now you see that everything with a node is in one column, and then you see here the frequencies in the columns, right? So I copy that representation, and then if you think a bit about that, this column, yeah, you can basically interpret as a vector, right? And if you say that the ith column is then this kind of a vector, it can, or always, you can always assume that it represents a point in the n-1 dimensional space, because I actually erase the 0 coordinates. This is not quite interesting. So you can actually draw, well, I draw it only in 2 dimensions. Yeah, this is it. Here you see then the 3 vectors. And you can actually show that these vectors, or you can reconnect those vectors together, and then they make a triangle, which is actually, well, a triangle is a simplex in dimension 2. And it means basically if any point on this edge or inside this triangle can be represented as a linear combination of my vectors S here. And in order to have them lying either on this line or inside the plane, we have to restrict the coordinates xi, or the linear coefficients xi, and that is the restriction. So in short, I'm going quite fast, I don't prove anything. This shows that any graph, and that's a theorem which is proven in Fiedler, and the book of Fiedler, well, it was before us. We independently recovered it in 2018, but he proved it already. And it means as follows: any connected undirected graph can be represented as a simplex. Here you see a simplex in 3 dimensions. You have 4, what you see here, vertices, right? Vertices. You have here edges. You have a face of the simplex, and this is a face which is actually generated by the 3 vertices, 1, 3, and you can say this is the same as the face, which is the complement, right, of node of 4. So this is actually the complement notation. It means that if you have 4 nodes in total, and you take here 4, this is the face that is, so to say, opposite or does not contain. This is the face that does not contain the vertex 4, right? Probably interesting here is that the edges correspond to the nodes in my graph, but the links do not. So an edge here is not a link, right? I will come later on to say what is a link. Now a little bit of mathematical, and I know this is a heavy notation, but it says that any face in a set of vertices V, and here I take the number of vertices, can be represented as a point, right? And the point is that my S matrix, which I found, and this is then the coordinates. These are the coordinates, and these coordinates are only non-zero for the vertices which belong to my face, right? And then I have that in total, that the sum of all those coordinates should be 1. That is just to describe in a system in which point or in which face, which edge or of the vertex I am. And this vector is called the barycentric coordinates. it takes you some time to really understand what it means, but I give an example. So if you talk about centroids, centroids are middle lines, right? A centroid is defined by taking the x coordinates very easy. You take them 1, right? And then here you divide them by the dimension of the set of the vertices of the face. Yeah. So they are that is the u. It is only 1 if the index here belongs to my set of vertices that defines my face. So if you now take here in a 2-dimensional thing and you take all the vertices and you take the middle point of all the vertices, then you end up by the s multiplied by the u vector, which is 0. Then you end up with 1.0. So it means that the middle point of my, and this is now simplex is a triangle, the middle point of my triangle is the origin. And it's actually a generalization. This can be generalized to any dimension, but it's a very simple proof of what Euclides already proved, that all the middle lines of a triangle meet in 1 point. Yeah? So this is not rocket science. Then you can actually see in centroids, you have here then these vectors. You can always try to find the middle point of between, this is an edge, right? And you take the middle point here, that is a vector which points from the origin to the middle point of that edge, right? So, and that is actually the centroid of a face. So the middle point, if you wish, of a face. And a face can be 1 dimension, then it's just the vertex itself, an edge is defined by 2 vertices, and so on and so on. So these are the centroids. Now the geometric representation of a graph, I want quickly to show you where the links do come from. Yeah? And then we need a couple of, well, first mathematical things. I showed already that this is the Gram matrix. And if you do then the computation, you can show that the scalar product of the S vector with the G vector is nothing else than the element of my Laplacian. Okay, so this one is a quite interesting interpretation, because if I'm now going back and I take the difference or the distance between 2 vertices, two vertices in my simplex, I can do the computation here, and I end up with the degree of that vertex plus the degree, and here you see the links appearing, because this is the adjacency matrix, and it's only non-zero if there is a link. It is 0 if there is not a link, right? So you can compute it differently, but geometrically what it means is, again, I have my simplex. Well, here in 2 dimensions, it's a triangle. I have my middle point, which is the centroid. I have the vector Si going to my index, my vertex I, and here my vertex G. And then I know that this length here, you do the computation here, you find that the length from the center of my simplex towards the edge I is nothing else, well, the length squared is the norm, the Euclidean norm squared is the degree. So this is the degree, and the angle between those points here, the angle between those points is the cosine, and this is, yeah, elementary mathematics. But if you fill it in here, right, and you use this equation, then you have minus here, minus the adjacency element here, if I and G are, of course, not the same. If they are the same, then it's only the degree, but if I and G are different, then this is the adjacency element. And that's cool. What does it mean? If there is not a link in the graph, then the angles are precisely orthogonal. If there is a link, the angle is larger than 90 degrees, because it's always, this is always negative. So, and if you combine everything, you can show with these kinds of insights that you have really simplex. Yeah? So I'm not going to go much further, because there is a wealth of nice geometry embedded in this representation. I just refer introductory to an example of us. and a couple of other things, that the spanning trees in a graph are related to the volume of your simplex. Cuts in graphs can be related to altitudes, and so on. Now I come back and I give you the practical example of a linear process, because, yeah, okay, I consider here now a linear process, which is also very easy. Yeah, you consider a resistant network, and you inject a current in one of the nodes. This is the node I, and I allow that the flow leaves the network in all the other nodes of the network in an equal amount. That's the setting. Okay, again, I inject in a network a current, and it's a unit current, and the unit current leaves the network in all the nodes in an equal amount. Since I have capital N nodes, it is, oh yeah, and I'm going to use the inverse relation here. I'm fond of this relation. Inverse relations pop up everywhere, actually in AI. And in machine learning, it's all about inverse relations. You have a lot of data and you want to understand what is the process, right? So inverse relations are interesting. So I use this inverse relations, and again, with a little bit thing, I have here an injected current in node I. So here the X that I have here is the unit current. It is the unit vector. It's all 0 components. Only the ith component is 1, right? And the current leaves all the other nodes, that's the U vector, the 1, 1, 1 vector, in an equal amount, 1 out of n, right? So if you put this vector into my inverse relation, taking care again that the U vector is an eigenvector belonging to the 0 eigenvalue, also for the inverse, for the pseudo-inverse, then you find that the nodal potential of the node I equals the diagonal element of my pseudo-inverse. Okay, this is the math. What does it mean? If you generalize, or you think you want to have everybody in a network informed in one person, and everybody needs to have the information, which is the person that you are going to use to inject the current, well, you can use the one with the lowest potential, because he is the most efficient one. Because potential multiplied by charge is energy. So the minimization of energy, yeah, gives you, in a very easy way, the finding of that node that is basically the best spreader in your network, right? So based on that notion, I define now the vector zeta. Zeta is the vector with all the diagonal elements of my pseudo-inverse, right? So this is actually an interpretation. If you look to a network, right, which kind of nodes is more central with respect to flow distribution or information distribution. So it gives you actually an idea of how important a node is with respect to spreading of information or spreading of diseases or spreading of everything, yeah? General spread. Now I give you an elegant geometric proof. If you go to the simplex structure, yeah, then we can show that the altitude in a simplex, and altitude means if you have here a vertex, right? And the altitude to all the other vertex, it means the phase in which all the other vertices are, and the shortest distance is the altitude. And here I put it because the altitude is then the shortest distance, or the line should be orthogonal to that plane, right? And if you do the computations, you find that the square again of the distance of the altitude from the point 2 to the plane here formed by the other vertices is 1 over the diagonal element of the pseudo-inverse of the Laplacian. Again, this gives you a kind of a geometric proof that these kind of nodes, that there is a sort optimality, right? That's a geometric proof. The other one was the energy optimization. And in short, what I give as an example, the zeta vector is, geometrically speaking, equally important than the degree vector, okay? So let's all now, I'm in half of my talk. Now I'm going to the stochastic linear processes. Okay? And I'm going to talk about epidemics. which is also spreading. First of all, I assume that most of you have heard about Markov processes. Markov processes are, well, the process on itself is not linear, but the probability that the process is in a certain state obeys a linear differential equation. And the nice thing is, you see the Q, the Laplacian, again, popping up. Here, unfortunately, because now I'm talking about the process, the Laplacian is not always symmetric. Generally, even it is asymmetric. And that is due to the process. Remember, the underlying structured graph, which was, well, undirected, but the process is making the directions. And here you see it. I will show you immediately an example which nicely manifests this. Okay, let us turn to the example of a very simple epidemics. You've heard it all in COVID, so what I'm telling now is probably a bit too easy. But I'm going to stress that I'm considering Markovian SIS. And you never wrote in the papers that they are talking about Markovian SIS processes, just SIS or SIR and so on. So what is it? It's very simple speaking. We have 4 nodes. This is the target node 0. You have 1 healthy node, so he cannot infect you, but the 2 infected nodes can infect you. And I take here for simplicity that the strength over the links is equal in all the settings. So anybody can infect anybody else with the same strength, right? That's what I'm saying here. So the infection rate beta on all the links is the same for simplicity, and also the curing rate. So the way in which you cure is the same for all the nodes. And in addition, I assume that both processes, infection and curing, are independent Poisson processes. That's important. Independent Poisson processes. Why is it important? Because Markov theory is actually the theory of independent Poisson processes. Yeah? So that's why I call it the Markovian setting. And then I have a kind of a control parameter that the ratio of the rates, the infection rate of the curing rate, I call the effective spreading rate. Okay, so this setting, you know, we are now in a network. And you've seen probably a lot of times susceptible, meaning that now, well, I define that a node actually has a health state, and I call it capital X. I use capitals for random variables, capital X sub A. So this is the health state of node G at time t. So if it is 0, then it's not infected. It is 1, it is infected. For single processing, I thought, yeah, you know this, then you have this kind of a series over time, infected, not infected, and so on. And if you know precisely for each of them the series, you can probably also go inverting that and trying to get the inside of the network. That's between brackets. What I now actually I'm interested in the probability that the node is infected, that's the probability of the state variable of the node I equals to 1. And that is basically what is physically important to understand. At what time of what is the probability that one of the nodes, one of you, for instance, gets infected via a contact network. An interesting thing is that this is a Markovian process where the state is only 0, 1. And the 0, 1 random variable is one of the simplest random variables. It's a Bernoulli random variable. A Bernoulli random variable has a fantastic property that the probability operator can be replaced by the expectation operator. Again, the expectation operator is a linear operator. And this is a huge and an important insight. I will show you very, on a physical way, why it's so important. But first, coming back to Markov theory, right? So, for instance, you start with an underlying contact network of 4 persons, and they are connected in one of these possible ways. I have here the dotted way of the links. If you use all the links, you have a complete graph, but you can pick out links and whatever. That's not so important. Important is that this is the structure of the graph, right? And in Markovian theory, you can show that the process is also again a graph. That's nice. You see both process and underlying structure as graphs. Of course, you see that there is a huge difference between the process graph which describes the Markov process. And by the way, any Markov process is a random walk on that graph. That's also interesting. Yeah, I will first give a little bit an interpretation of the graph. You see here that each of the nodes here, you see here the digit operations. I have 4 nodes, and each of the nodes can be either infected or not infected. So the total state space is already 2 to the power n. That's annoying, very annoying, extremely annoying, right? Because it blows up exponentially with n. Yeah? And then you see here, if they are all healthy, yeah, 0 means you're healthy, then the decimal representation of the binary digit is below the states. But if they are all healthy, then you're in the absorbing state. Why the absorbing state? Because the epidemic stops. There is no epidemic anymore. It leaves. So this is a process where in an absorbing state, everything stops. And what is also nice is that even here we take reinfections into account, that any finite infection virtually always will stop. Because this is continuous time. Yeah, but here in continuous, that's a very interesting observation. In continuous time, Markov processes do not allow that. In continuous time, there is at any point in time with overwhelming probability only one transition. And that is why in continuous time, which is, by the way, much more physical because time is not discrete, time is continuous, this process is easier, right? Because due to the fact that it is indeed in continuous time, and you go here well, I organize it per line. So here there are no infections. Here in this line, in the network, there is only one node that is infected. The first node, the second node, the third node, and the fourth node. Here there are 2 nodes that are infected. Here there are 3 nodes and 4 nodes. And you see also that the number of them are just the binomial coefficients, right? And you see that the interaction due to your, the interaction is only from one layer up or one layer down. If you have a healing, right, then one of those bits turns out to be a 0. If you have an infection, one of those bits turns from a 0 to a 1. So there is a lot of structure. This is, by the way, a beautiful Markov chain, I find. The only thing is that it's 2 to the power n states. Yeah? And you, well, in Markov theory, your problem is solved if you can draw this slide. Yeah? If you can draw the Markov graph, you're done. Right? Then the other thing is just applying the methods and finding whatever that you need. But if you don't have this picture, you don't have anything. Yeah, this is actually the translation of the physical process to the Markov graph, and that's an essential step. What I wanted actually to say to you is that there is a very interesting physical insight related to the Bernoulli random variable. Because what do you see here? You see here actually the time change of the probability, because remember, again, in the Bernoulli random variable, the difficult operator, which is a probability operator, it's difficult, is replaced by a simple operator, which is a linear expectation operator. So I change here the probability operator by the expectation operator, and then I put the expectation operator a little bit outside my brackets, and just look inside your brackets. Inside your brackets, you see a very beautiful physics appearing. What is this one? If you are infected, so my random variable is 1. If it is 1, it means that this term doesn't play a role, right? If it is 1, you are infected, you can heal or cure with the rate minus delta. Why this minus? Because your probability to get infected goes down because you cure, right? Okay, the other way is, if you are infected, this term doesn't play a role, yeah, because it's 0. Only this term plays a role. And then it tells you if you are not infected, so you're healthy, you become infected by the sum of all your neighbors that are infected. Because a neighbor that is not infected doesn't play a role, only those that are infected. And the strength is beta. Come on. You're all engineers. This is beautiful, right? Because what do you see? You have a complicated if-then-else rule, which in binary notation gets just a sum, and then you're done. This is the complete physics. If you then do the mathematics, meaning that you introduce your expectation operator, then you write it as this one. That is not rocket science, but you see that there is a complication here. Yeah? Because by doing this, the interaction with the others incurs that there is a complication. You need the joint probabilities. And I don't have the differential equation for the joint probabilities. That's not a problem. I can write the same thing here, yeah, the same physics for the joint probabilities. I can reason. And of course, you can continue. And if you do it in the right way, you end up with 2 to the power n linear differential equations. In other words, this is another physical insight of what happens in my Markov chain that I showed you before. The advantage is that this exact equation can be approximated in a very interesting way. And the way comes from basic physics, from quantum physics, basically, because quantum interacting particles have the same probability of the exploding state space. And there, the best approximation of the random variable is its mean. So if you replace here the random variable by its mean, and I call it now W, you end up here with an equation which is a deterministic equation, which is actually a transition what we made from 2 to the power n linear Markov equations to n. And now you see that it is non-linear because you see here the W and you see the W there. You have a non-linear mean field approximation. I call this a very beautiful approximation. I called it Nympha. It's like a goddess, and it's really amazing. By the way, you can deduce a lot of things here, and during COVID, you've only seen things in the public by this kind of an equation. So what does it mean? This equation, or the process, I give now an interpretation physically what it means. I'm interested now to know in the entire population, what is the fraction of infected diseases? Because I would like to know, are there many people infected, yes or no, right? And so the prevalence equals the average fraction of infected individuals in my network. And then I have here the strength of the virus. I did simulations, and the red lines are exact simulations or computations even. And you see then for a node of, well, a population of 25 people, then you see 50 people, then you see 100 people, and this is the effective strength. And you see here in the dot line and the dark line, you see the mean field approximation, which is here upper bounding, and you can mathematically prove that it's always an upper bound of the infection rate. So what else do you see is, you see actually a clear cut after, this is the situation after sufficiently long time, right? In a kind of a steady state situation. And then you see that here for effective strengths which are very low, so the virus is not strong enough, then it dies out. Yeah? So the virus is extinct, and above the line, the virus keeps, well, I used it terrorizing, comes from Corona, right? The entire population. What is also interesting is that the corner point here can be precisely, well, it can be lower bounded by the Nympha equations, by the nonlinear differential equation. And you find that this corner point here, the strength, remember that tau was the strength of the infection defined by the strength of the healing, right? Is just 1 over the largest eigenvalue of the graph. That's also beautiful. So the corner point is related to the structure of the underlying graph. So that's important. If you now normalize the effective strength and you multiply the effective strength by lambda 1, right? Then lambda 1 equals the reproduction number. And that's the number you have seen over and over again, right? And it was the control parameter, the control parameter. If the R naught is below 1, then nothing happens, we are fine, it will die out eventually. If it is above 1, you have an exponential increase. So it was always the target to get the shift of the R naught below this point. So this gives you an ID where all the stuff comes from. It is the Markovian ID, right, that led to the mean field equations. The mean field equations gave you the control parameter related with your underlying graph, related on the reproduction number, which should be, well, below 1, right? This is all Markovian. Yeah? Before going to the non-Markovian and telling why this is an idealization of the world, I would like to point to you that a lot of processes in physics are all from this type. And I call these processes the local rule, the global emergent properties. And what does that mean? You have, again, a contact graph or a contact or an interactor. It is a graph where items in the graph interact with each other. And simple, if I take now the process, the SIS process, what happens is that the local rule is very simple. You can program it. It is what I said to you. It is as long as you are infected, yeah, until you are recovered, the only thing you have to do, infect your neighbors that are still healthy. And everybody is doing this small rule. And due to the connection with the entire underlying graph, the interconnection makes that the process is overwhelmingly complex. Yeah? And this is the equation that I derived rapidly for you. This is the NIMFA equations. Now, if you look to other types of local rule, like synchronization, the flock of birds, swarm of fishes, they're all the same, right? A bird in a flock of birds, they are just positioning themselves or the fishes, and then the rule is keep a certain distance and keep up velocity, right? And the rules are very simple, but still the swarm can be amazingly complex. Yeah? And this also inside, which is mathematically written by a similar type of equation, what you see here. Yeah? You have here the local dynamics, and here you have the interaction dynamics. Okay? And what is nice in these processes is that if you look to the network, it is again linear in the network. You see the adjacency elements here, they come in a linear way in the network. Okay, let us switch then shortly to the non-Markovian. Why I'm still amazed, and you also have seen it in COVID, that although the prediction of the R naught was given by a number, it not always corresponds with reality. And is that amazing? No, of course it's not amazing. Because the underlying, or one of the very strong points in Markovian epidemics or Markovian theory is that the time between interactions, which are Poisson processes, is exponentially distributed. Yeah? So it means that we inherently assume that if I infect you, that the time of infection is an exponential random variable. Is that true? Well, unfortunately, it's not. Here we measured 10 years ago, Twitter, it's now called X, but at the time it was Twitter, the infection time in Twitter, right? And so we did more than 10 million tweets. And what you see here is the time in a tweet. Normally, if a tweet comes on your machine, you hear a beep, yeah? Notification that the tweet is there. Then you read the beep, and the reading of the beep is actually a kind of a time delay. And then if you read it and you say, well, this is a cool tweet, you retweet, right? So the infection time is actually the sum of these two parameters. And the network time is so damn small, it's instantaneous that I ignore it, right? If you then do the measurements, then you see that you can very nicely, and I still find it amazing, you can very nicely characterize the epidemic time or the time that you get infected by the convolution or the sum of two log normals. And the sum of two log normals, that's what you see here. So it is amazing that people actually react people reactions is actually basically look normal. And we see it in many other manifestations that we react as humans in a kind of a look normal way. But anyway.
Twitter spread is regulated by an algorithm. So not every tweet is going to see the same probabilistic rule. Actually, it's very different. They can shadow ban you and your tweets will never go further than your friends or something like that. So
yeah, but these are only based on measurements we had from a part of, and at that time Twitter was open. We could use, I remember, a certain amount of tweets which were open for use of academic purposes. Nowadays, I don't know it anymore. It was more than 10 years ago. But anyway, this is just a probability distribution, and this, what we measured, is reflected here. The only point that I'm making here is it is absolutely not exponential. And absolutely not, because these are a heavy tail distribution. This is a logarithmic scale. This is absolutely not exponential. Yeah, that's the way. But these are digital infections. Yeah? Real infections are very difficult to measure. But the few measurements we have also indicate that they are not exponential and that it can be modeled well in some way or another because the data is bad by a Weibull distribution. And here I write the Weibull distribution, and the parameter which is very important is the shape parameter. The B parameter is an average. And if you compare it with the infection time of the Poissonian or the Markovian case, then we have actually a pure exponential here, which is beta. And if we do a fair relation, we should actually have here that the beta or the average time of infection should be the same of all the processes, and it's 1 over beta. And that gives you an equation to find here the B. Anyway, if you now show the curves as a function of time, this is the probability density function of the infection time, then you see if alpha is 1, if alpha is 1, we have the Markovian case, that's cool. Then you have here the black line. If alpha is smaller than 1, you have these purple lines, and you see here that they go, well, for very small time to very high numbers, and they fall off like a power law tail. If the alpha is larger than 1, then you get here bell shape, and if it's more than 2, you end up with Gaussian or Rayleigh distributions, which are quite different than the power law structure for small n. So we have actually a tool by changing the shape parameter, given that the average infection time is the same, we can actually see what happens. So we did that. And if you do Markovian, and you have again the effective infection rate, and then here you have then the prevalence. You see here in black line the Markovian SIS process. And if alpha is smaller, you see that here the threshold gets very small. If alpha gets larger, the threshold is very large. In other words, if you relate this to the influence of the underlying graph, the process here is way more important. So it's always already kind of a surprise how all these agencies were able to compute the R0, right? Because if the R0, and we know it, it's not exponential, you should have a serious deviation from actually the truth. Cool. At this moment, I'm still thinking, okay, reality is not Markovian, so can we have a theory that is computable, right? And that is a little bit more close to, and here I was amazed to find fractional calculus very rapidly. You start here with a Kolmogorov equation, you replace the derivative by the fractional derivative, right? You have this kind of a differential equation, and the thing what was appealing to me is that it has an exact mathematical solution. And this exact mathematical solution is written in terms of the Mittag-Leffler functions. So, fine. So that was my target, and what is currently the target to focus on, because here we have the exponential base as eigen functions, and here the underlying base are the Mittag-Leffler functions. There are some complications what we are trying to solve, but the Weibull and the Mittag-Leffler function are quite alike here for reasonable, realistic parameters of the time. Although the Weibull random variable, none of the moments in the Mittag-Leffler function random variable, none of the moments exists, which is a peculiar thing, right? While in the Weibull distribution, all the moments exist. Okay, let me conclude. I'm on my time. I showed here that the semi-definite nature of the Laplacian gives rise to very nice, beautiful elementary or, well, linear algebra informations, as well as the simplex geometry. I show that Markovian theory with exponential time and the memoryless properties is extremely powerful. And I just keep saying this, it's extremely powerful. However, for linear system, it naturally leads to an exploding state space 2 to the power n, which is not possible. Because if I have a population of 2 to the power, well, 50 people, 2 to the power 50, no computer on Earth can solve anything. And it is still important because everything happens around that control, around the phase transition. And what I showed you here is that the mean field is very bad, completely bad around the control thing. So that's still actually a focus to get a little bit more closer. And then Markovian theory, we have general times. The history matters because it's not memoryless anymore, which makes the process extremely complicated. And there is still room for very elegant mathematics there. Okay, I thank you for your... Thank you.
Any questions?